we'll begin with where we left. So, the last step that we wrote down was go back to the wave equation in the transmission line, take the voltage wave equation and write that down in the difference form. And when we write this down in the difference form, we will have to look at what is the unknown quantity, bring the unknown quantity to the left side, all the remaining quantities to the right side. And what I was mentioning yesterday was in these kinds of equations, it's a good guess to begin with the unknown quantity which is in future, that is T naught plus delta T is the quantity that you want to determine. All the other quantities are known. So, T naught denotes current instant of time, all right, and T naught minus delta T includes the past. So, T naught plus delta T is what you want to determine. Okay. So, given current and past values, you would want to determine what the voltage values are. Okay. This is the way to formulate this problem. So, one can go ahead and actually write down what the unknown quantity would look like. So, I will just rearrange this. So, we have V at position Z naught, T naught plus delta T is the quantity that we are interested in. It is minus V Z naught T naught minus delta T plus 2 times V of Z naught comma T naught right, plus U square delta T square by delta Z square times the quantity inside the braces. So, you have V of Z naught plus delta Z comma T naught plus Z naught minus delta Z comma T naught minus 2V. This is what the rearrangement looks like, all right. And we can go ahead, open our computers, fire Octave. I will begin the code with the standard statements to close all open windows, clear the workspace variables and clear the display buffer in the command window. Right. So, now I am going to make a programmatic version of the equations that we just saw. Right. So, I am going to start with the definition of variables. I am going to say delta Z is what we assume to be 1, delta T is 1, okay, and consequently the velocity u is going to be 1, all right, because delta Z is 1, delta T is 1. So, in this case we are going to take the velocity to be 1, all right. I am going to now take the length of the transmission line to be some 30 units, all right. So, it is like 30 pieces. So, you can say that the transmission line is divided into 30 cells, each of them consisting of an L and a C in the form of a ladder that we made. Right. So, I am going to say that in this space the transmission line is spanning 30 units, right. And I want now this is a simulation for time evolution of voltages, right. So, you will have to start at some time, end your simulation at some instant of time, right. So, we have to tell what is the ending time going to be. So, I am going to say that some time is equal to 30. I will even begin with smaller values of time. So, right. So, the voltage is going to be a 2-dimensional matrix, right. It is going to look like this. Initially, I do not know the values of voltage at all points in space and at every instant of time. So, I am going to initialize it to zeros for all instants of time and for all locations in space. Okay. That is how we initialize. So, it is going to be a 2-dimensional matrix. For every instant of time, I am going to have a voltage value along the transmission line length. Okay. So, the rows here represent the space, the columns here are represented by the time. Okay. Now, I will go to the actual part where we need to write down the solution. So, if we look at the expression that we have here, we will need to start at some instant of time, all right, and we have to continue to evaluate with respect to current instant of time, what is the value of the voltage at the next instant of time, right. So, we have to start with the values on the right hand side here, all right. Initially your T naught is going to be 0, then you are going to have some delta t which is 1 in our program. So, every instant of time you are going to be calculating at a position and some instant of time based on the values of the voltage in that same position and in neighboring positions and past instants of time. We just have to take this and code it in our program. Okay. So, I am going to use a for loop to achieve this, so, right, for t equal to by now you would already have guessed why I am using 2 to time minus 1. When we solve for the Laplace equation, we know that when we are taking central difference, you will go with array index out of bounds. So, you will have to start with the value next to the boundary and end with the value prior to the boundary. Right. Okay. And I am going to have for all points in the transmission lines in space, you will need to calculate the value of the voltage, right. So, I am going to go ahead for z equal to okay, and inside this loop I am having a time loop that takes care of T naught plus delta t and keeps going till the end of the time that you have specified, all right. And at all instants of space, I mean at all positions in space for every instant of time is when we are calculating the voltage over here. Right. All I need to do is take the equation, now plug it into the form that can be easily programmed over here. So, I am going to have V of z comma t plus 1 is what I am looking for. So, instead of writing t plus delta t or t naught plus delta t, all right. So, I am just writing the current instant of time is going to be t in this loop, the next instant of time is going to be t plus 1, right. That is all I am interested in finding. So, V of t plus 1 according to the equation what I have is minus V of z comma t minus 1, that was t naught minus delta t in the expression that we wrote, all right, plus 2 times V of z comma t okay, plus I had some term u square delta t square by delta z square, all right. In this case u square is 1, delta t square is 1, delta z square is also 1, but for the sake of completeness I will go ahead and put that also in the formula. Anyway the coefficient is 1, one may choose to ignore it, but in future I may make use of it for some other purpose. So, I will just go ahead and plug in those values, right, u square to delta t square divided by delta z square, okay, and I have some terms inside the curly braces what we have written, right. So, I will go ahead and do this as V of z plus 1 comma t plus V of z minus 1 comma t. So, these terms comma t means it includes the current time instant value at that particular position, right, minus 2 times V of z comma t. Okay. All I have taken is taken the expression that we have derived and I have just plugged it in a programmatic form into the program, all right, what we are writing here. Okay. Once we have done this, right, the essence of the program is already over. It is now about how to set up this program to work, that is it, right. Like we have seen in the case of the Laplace equation, at every instant of time I would like to watch what is happening in the transmission line, right. Suppose I launch a voltage at some point, I would like to know how the voltage is traveling through the transmission line with respect to time. So, at every instant of time I need to have a display that tells me what the plot of the voltage with space looks like. So, I am just going to go ahead and have a plot command, right. So, I am going to be having plot the voltage at all points in space and the new calculated voltage now. Okay. And we also know that yesterday when we were looking at the previous lecture, if we do not give a pause command, then chances are that you will see one plot at the end of your program rather than seeing at every instant of time. So, I will just use a pause of 0.1. Okay. Okay. Now, everything is ready except that there are some small details that we will have to fix. Okay. In the case of the Laplace equation solver, we did see that we had set up some conditions. For example, the top plate is at 10 volts, the remaining plate were at 0 volts, etc. Here, you are trying to solve the wave equation, right, but we have not provided any source of the wave. We have to define the source, we have to define where it is going to become 1 volt or 2 volts, etc., and then watch it with respect to time, right. So, I am going to provide that information over here. Okay. So, I am going to say that just going to place this in two places. So, in line number 8, I am saying that V of 2 comma colon is equal to 1. So, the spatial location of 2, okay, for all instants of time is going to be at 1 volt. So, in other words, I am plugging in a battery there of 1 volt, it is going to be delivering 1 volt at the position 2 for all instants of time. This will become apparent if I run the program. Okay. And what happens within the loop is there is a chance that because I am writing in this form, I may actually update that to something else, because I am calculating the value of voltage at the next instant of time. At any instant of time, I want the battery to give me the fixed voltage. So, I am just making sure that I am plugging in V of 2 comma colon is equal to 1 again. So, now let me just go ahead and run it. Okay. Now, let me do this in a little bit more elegant manner. So, I will give an access command. Okay. So, here what is happening is at some instant of time in the beginning, alright, for all instants of time you are going to be having position 2 to be giving out a voltage value of 1 volt. As time increases, you are just solving the wave equation, and the wave equation is telling you that the wave is traveling inside the transmission line, right. So, at 20 instants of time, it is going to have a velocity of 1 cell per unit time, that is, it is going to travel delta z distance in delta t time, because its velocity is u, which is equal to 1. So, at some instant of time, it reaches to the spatial location of 20. This is the way to look at the wave equation for the voltage, right. If you did give a source, it is going to solve and it is going to tell you that there is going to be some wave front that is traveling along the transmission line. But some funny things happen in this, and that is why I wanted to start in detail. I am going to increase the amount of time that I need for the simulation to say 40, okay, and I am going to run this again. I am going to notice that the voltage is going to the end, and then something else is happening. Suddenly the voltage in the transmission line appears like is doing something very vague, alright. It was supposed to have 1 volt throughout the transmission line, but okay, something is happening, right. It is clear that the voltage cannot become suddenly 0, alright. This part has to be understood more precisely. You had a forward voltage of 1 volt. On the right hand side end, what could have happened is there was a reflection, and the reflection is now has to be understood in more detail. It just didn't reflect 1 volt, it actually flipped the 1 volt in sign and then sent it back as a backward wave, and you had a superposition of 1 volt traveling forward and minus 1 volt going in the backward direction, and the superposition was actually 0. Okay. So, now we understand that the wave equation, depending upon the boundary condition, can tell you at least programmatically whether you are going to be having a reflection or not. Secondly, we also understand that the reflection is not only going to tell you something about the amplitude of the wave that is being reflected, it is also going to consist of a sign change. Okay. So, this is a very important thing, but other than that, it is a very simple scenario, right. Suppose I make this for, I could do things that I cannot do with a real transmission line very easily. For example, I could say that the voltage at position 12 at all instants of time is equal to 1. So, this means that in the middle of the transmission line I am connecting a source. Normally one would not do it, but it allows me to do this. So, I can play with this program and try to make deliberate changes and see what happens, alright. So, I would like to do this first, right. So, I noticed something, right. This is the way the voltage is going to be inside of the transmission line. It is not what one would expect normally. It is not just that you would send 1 volt and you will have 1 volt everywhere. First of all, when we began the program, we noticed that from the position there was a voltage wavefront traveling to the right side, there was another voltage wavefront traveling to the left side. They go and hit the boundaries, and depending upon the boundary conditions they get reflected. They can also have sign change in reflection. Due to this, at this instant of time where we have stopped the simulation, the voltage profile across the transmission line looks like this. There is a voltage of 1 volt in some portion, the remaining portion of the transmission line has 0 volts. Okay. Now, this needs a little bit more care, and it tells us that we have to look at transmission lines in terms of reflections. We have to understand in steady state what is going to be the voltage in transmission line, alright. We also need to understand, if you detect a 0 volt in transmission line, does it mean it is really carrying 0 volt, or does it mean that there is a forward voltage and a backward voltage superposed that is giving you 0 volts. All these things have to be considered in great detail, alright. But this is a good starting point, alright, because I have touched the word reflection. Now, we will go back and look at what all we have done and where we are getting, alright. So, initially we started with simple transmission line equations, alright. We made a model which was lossless, and it gave us some partial differential equations for voltages and current. Okay. Once we had the partial differential equations, we tried to make the wave equation, alright, and we tried to use some general solutions to the wave equation and found out that the voltage and the currents can actually be traveling in the form of wave. At that stage, we did not know what to do with it more, alright. So, we taught ourselves how to use a computer to solve partial differential equations. We started with representation of first and second order partial derivatives, and then we, as an example, we solved Laplace equation. Now, we did not do very big change from the Laplace equation to this, and we are already able to solve wave equation. The only thing that is remaining is finishing what we started, alright. We still did not solve telegraphus equations. The telegraphus equations were 2 in number. Once we finish that, the remaining parts are going to be a breeze, because you will have a visual understanding of what the telegraphus equation actually mean. The difference between the wave equation and the telegraphus equation is, the wave equation is decoupled, that is, the voltage is there on one side with respect to time you take derivative, on the other side you take with respect to space, but you do not observe what is going on with the current at the same time, alright. So, the only thing that is pending for us to complete this particular exercise is to go for solving the telegraphus equations in its form that we have written. Let me go ahead and do that, alright. So, I will start with the first equation, dou V by dou Z is equal to minus L dou I dou t, right. This was one of the telegrapher's equation that we had. Now we have an idea about how to write these derivatives, right. These are first order derivatives and we could use forward difference, backward difference or central difference. Thus far I have been using central difference for all my programs, alright, but I am going to give you some confidence that I am going to be using forward difference, alright, and I am going to be using backward difference to just illustrate that I could use either of them, right. So I am going to write down the left hand side derivative, alright, with respect to space. So I am just going to write this as v of z plus 1, alright, or z plus delta z, okay. But since I am going to translate this to a program, I would like to be close to it, alright. I am going to divide the space into units of 1, delta z is going to be 1. So I am just marking as v of z plus 1, alright. It is also having time component present over here, right. So I am just mark this as t minus v of z comma t divided by delta z. So I have used forward difference for the spatial derivative on the left hand side for the voltage, okay. On the right hand side I have minus L, L has to be a quantity that is given to you, right. In all our programs we are assuming L to be equal to 1, right. We are starting with some large values, right. And for dou I by dou t, alright, let us write this down in terms of forward difference in time, right. So this will become minus L z of t plus 1 okay. Once you have written in this form, you should immediately be able to understand based on what we have discussed, the unknown in this particular equation has to be the quantity in future, alright. And if I look at this equation, I have a quantity in future I of z comma t plus 1, that is the unknown quantity, bring it to one side, push all the other quantities to the right hand side, okay. So rearranging this, you will be having I of z comma t plus 1 is equal to I of z comma t minus delta t by L delta z v of z plus 1 comma t okay. This is going to be the difference form of the first telegrapher's equation, okay. So I of z comma t plus 1 is the quantity that you want to calculate. I of z comma t is the quantity that you are already aware of at the current position, and then you have to take some voltages at neighboring points, okay. Now let us also write down the difference form of the other equation, the telegrapher's equation. So that would be dou I by dou z is equal to minus C dou V dou t. Okay. In this particular case, just to mix up things, I am going to be using backward difference for the space on the left hand side. It may look very confusing. I just want to convey that you could use any of them, alright. There are some catches. I will not go over the catches in this course because there is an advanced course in computational electromagnetics that you can always do in a later stage, alright. But I think there is no harm in using a backward difference. You are using forward difference in one case, we can use backward difference. So I am just going to write this down as I of z comma t minus I of z minus 1 comma t divided by delta z. This would be the backward difference for the spatial derivative on the left side, and on the right side I will have minus C dou V dou t. Now it is very clear that you would not prefer to use backward difference for time, because you want to estimate the quantity in future, you need to have t plus 1. So the choice is obvious that you will have to go for forward differences for time. You could also use central differences on both sides. So since we have used central difference 2 times, I am just doing this with forward difference, okay. So I'll be having minus C dou v dou t will be t plus 1 v of z comma t divided by delta t. So looking at this equation, we now know what is the unknown quantity. Unknown quantity is the quantity that you want to calculate from the future. That means the t plus 1 subscript has to be there, right. So that quantity v of z comma t plus 1 goes to the left side, right, and you have the current value of voltage z comma t on the right side minus delta t by c delta z. Now let us pay a little bit of attention to these equations and what is the strategy to solve these equations to make some sense. Okay. First of all, the wave equation was decoupled. That means your left hand side and right hand side has the same voltage or current, right. But here the left hand side for the first equation that we have, right, is going to be dependent on the voltage at current instant of time, and the voltage in future is going to depend on the current value the current instant of time. Now these equations are not independent, they are coupled partial differential equations, and we have not solved coupled partial differential equations before in this course. Okay. So we need to know a strategy on how we are going to do it. So the way in which we are going to do it is, for any given position, let us say that we will calculate the current first. So I have written this equation first. Let us say that I have some boundary conditions or I have some source conditions given. So but I will be calculating at a given position, I will be calculating the value of current at the next instant of time. Once I calculate the current at the next instant of time, all right, that current has to be used here in the bottom equation to calculate the voltage at the next instant of time. So coupled partial differential equation here means that both have to be solved, all right, one after the other, and the solution that you get from one has to be plugged into the other. This gives rise to some serious thoughts. Okay. When we were trying to solve this equation, t plus 1 was the future over here, right, I of z comma t plus 1 was the future, but once you have solved, that is your present value, correct. I mean, once you have finished solving, you have estimated what is your current value. Then you have to plug the t plus 1 whatever you had for current, you will have to plug it as I of z comma t, and then you end up solving voltage for the next time instant for when you calculated current. Okay. What ends up happening is that you will keep calculating current at one instant of time, voltage at the next instant of time, current at the next instant of time, voltage, and it keeps going like that. You are going to be solving in a in a manner that was different from your Laplace equation or wave equation. You are solving two equations and they are coupled. That means you have to take the solution from one and plug it into the other. This takes some time to understand, but these are not independent equations. So your t plus 1 here, the quantity of current that you calculate, once you have calculated, becomes the current value of the present value of current that you are aware of. So this has to be used as the present value. Once you have calculated voltage of z comma t plus 1, you will have to go back, plug that as the voltage at current position and current time. This is what it means by doing the coupling. So you have to do this back and forth, all right, and this will this will become familiar once we write down the code for this. Okay. So I will go ahead and write down the code for doing this, right. And it has some specific advantages over the code that we have just written for the wave equation, right. So, I start with the standard statements, close all, clear all and CLC. Right. Now, I am going to define my transmission lines in the way we had seen in the earlier theory classes. I want to say number of sections that are going to be present in the transmission line. Right. We are going to start with 100 small sections. Okay. So, I am assuming that the transmission line is chopped into some small 100 pieces. Right. So, I am going to define my voltage. Now, I am making a slight change in the strategy. Okay. Previously, the voltage in Laplace and the wave equation, right, I mean especially in the wave equation when we were using this voltage, we tried to use two dimensional matrices, all right. It consumes more memory than doing a one dimensional, all right. And I am looking at this each time after I finish plotting, I do not have any use for the stored value, all right. So, at any instant of time, I am going to be storing the value for the current time step, all right, and I am going to be using that, I am going to be overwriting that again and again. What that means is, if I have a look at the equations that we have arrived at, V of z comma t plus 1 is V of z comma t minus some quantity, all right. This is your present, this is your future. All it is saying is the future value is the present value minus something. Okay. So, I can just say that I will rewrite the future value in this present value itself, right. It is like writing A is equal to A minus something, that is all. So, all I need is to store one instant of time, and I am going to be able to calculate the values of the voltage and the current. The same thing is going to be having for the current, all right. It is a present value plus some term on the right hand side. So, I can just say the future value with the same variable name is present value plus something, right. That is how we are doing. So, we are trying to use a little less memory than before. So, we are making progress in the way we are doing the coding part. All right. Now, unlike the wave equation, we also need to define our current, right. Current is going to have the same dimensions as the voltage vector that we have defined. Okay. And just to be clear and consistent with the class notes, all right, I am using a ideal lossless transmission line, and I am just assuming L to be equal to 1, whatever units you want to plug in, you can plug in, right. C is equal to 1, and the value of the velocity, all right, is 1 by square root LC. So, here it is obviously going to be equal to 1, right. So, I have not put any units because my unit of space is going to be delta z, my unit of time is going to be delta t, that is it. Okay. I also have to specify a few more things. I want to start at time t equal to 0, all right, and I want to be able to finish at say 80 future time steps. Okay. On top of this, I have to give the delta t value because my update equation has delta t, delta z, etc. on the right hand side, right. So, I am just going to make the life simple, choose everything to be equal to 1. Okay. So, most of the definition is done. All we need to do is now plug in the equation that we have made using finite differences into these loops, and then we can see what is going to happen. Then we will have to compare what is happening here with the wave equation and then try to see what more we can get from here, right. So, in order to do this, you will need to have a loop in time, right, for t is equal to t start colon delta t colon. So, I am being a little bit more precise. Previously, I did not use t start colon delta t colon t end. I said that in the case of octave, if you do not give the middle argument, it will keep incrementing by 1. Here it is the same, but I am just being more precise because we are making progress in the way we are coding, right. And for all points in space. Right. For every instant of time, for all points in the space that I am having, I would like to calculate the values of current and voltage, right. So, we wrote down the current equation first in our notes. So, we will do the same thing over here, right. Please understand that the way I am coding, I have removed T as something needed from the array index because it is a one dimensional array now, alright. Whatever is on the left hand side is the future value, whatever is on the right side is going to be the present and past values. I do not need time index at all, okay. So, it will take some time to understand this, but these are slightly different from the equations before. These are known as update equations. You are taking the current value and adding something to it to update. Okay. So, the way we had written was I of z future value, this would have been written as I of z comma t plus 1 in our notes, okay, is equal to I of z, right, minus the quantity was delta t divided by L times delta z multiplied by V of z plus 1 minus V of z. This is the equation that we had written down. I just want to make sure it is the same equation that I have written. Okay. So, delta t divided by L delta z V of z plus 1 minus V of z, okay, looks the same. Okay. So, once I have calculated the current in the same time step, I would like to calculate the voltage. So, I am having V of z is equal to V of z minus, right, delta t divided by okay. So, we had used forward difference in one case and a backward difference in space for the other case, right. And the way we have written it, we have actually coded it. So, this is your telegrapher's equation code. All we need to do now is set it up a little bit, that is, we need to give a source of a voltage or a current or something in this transmission line. Then we have to give some plot commands to plot the current and the voltage, and then we can start to go back and see what is happening, and in the next class we can go back to some theory on what happened and build on top of things. So, let us go ahead and finish this. Okay. So, at every instant of time so, the subplot of 2 comma 1 comma 1 just says that it is going to divide your screen or a plot into 2 rows, alright, 1 column. When you divide your plot into 2 rows and 1 column, you will be having a plot on the top of your screen, plot in the bottom of the screen, 2 rows, 1 column, because there is only one on each, on the top and the bottom. And then once you divide it, you have to call it as plot number 1 is on the top, plot number 2 is the bottom. So, subplot of 2 comma 1 comma 1 means that I am dividing it into 2 rows, 1 column, and I am going to be talking about the first one on the top. Okay. So, I would like to have this because I would like to plot the voltage on the top and I would like to plot the current at the bottom. Previously, in the case of wave equation, we could plot only one quantity at a time, right. Now, I can plot both the quantities, right. I can plot voltage and current, and I can draw different inferences from what is happening, right. So, I would like to plot voltage, right, and I would like to plot voltage in red color. So, that single quotes R just tells you that plot it in red color, right. Okay. and so the axis command here tells you it's of this form. Axis within square brackets, what you're giving is x min, x max for the x axis, y min, y max for the y axis. I want to specify this because I saw already in the wave equation that when reflections happen and all that, the value of the y axis keeps jumping here and there. I want to keep the y axis fixed so that my concentration is on the voltage or the current quantity. So that's what we had used in the transmission line equation also. We had given an axis command. All right. If we don't give this, it keeps going up and down. The axis scales depending upon the current value of whatever voltage or current you have calculated. So I want to keep it fixed. Okay. So I would like to plot voltage on the top plot. All right. Then the plot below. So I'm going to say 2, 1, 2. So it's second. The plot is divided into 2 rows, 1 column, and I'm addressing the second plot. All right. The second plot, I want to be able to plot I. It's okay if it is in default color because I would like to distinguish between the two, right? And I would like to give an axis which is going to be the same. And as usual, some pause command for me to actually have a look at each and every instant of time what's happening. Now everything is more or less set except that we have not defined our source, that's all, right. So we'll go ahead and define our source. Okay. In this case, the previous wave equation case, the kind of source I had defined was it was on all the time. It's like a battery. You have closed the switch at t equal to 0 and you are solving wave equation trying to find out what the solution will look like. Okay. So in this case, we can do the same and we can do many other things also. So I'll go ahead and do something which is slightly different. Okay, so that you get a feeling for the amount of variety that one can do. Okay, this is also a kind of a definition of the source. What I am doing here is at the instant t equal to 2, I am making the voltage at a specific point go to a value 1. At all other instants of time, that point will be 0. In other words, it's like giving a impulse, okay, at some instant of time and then 0 volts, or it's grounded at the all the other instants of time. I just wanted to plug this in because you should know that the way we have defined the sources, we have flexibility over that. We could do impulse, we could do rectangular, we can do sinusoidal, we can do many things. Okay, so it just needs to register in your mind that you can play with all of these quantities. I'll just go ahead and run this once to make sure that the program is running. Okay, it is indeed running. Okay, now many weird things will be happening and that is going to be the subject of our discussion as far as the theory goes. Now that we have completed one complete loop, we started with analytical part, how to develop a model. We wrote down the partial differential equation. We wrote down the general solutions. We also verified what is going to happen with the computer. You should have a decent understanding of what's going on with the telegrapher's equation and the wave equation. But now let's use this program to drive the theory forward. Okay. So let's see what happens when I do a few things and then decide how to carry on the theory. All right. So I'm going to start with ending time of the simulation to be 40 seconds, right, or 40 units, so or even 30 units, right. So I'm going to start. So the red color on the top represents voltage and the blue color represents the current at the bottom. This information was not present to you in the wave equation case. Now you are watching current and voltage in the transmission line. Next thing that I notice is I had set my source in the center. Regularly in transmission line you may not be able to do this, but for our understanding we could do this in a program, right. I set an impulse at some instant of time and the impulse traveled in the left and in the right in the transmission line. Okay. So, the voltage is going from the center to the other side, but notice the current, it is travelling to the right side with a peak at 1 and it is travelling to the left side with a peak at -1. First of all, this information was not available to me before when I was solving the wave equation, right. Now, this is a new piece of information, correct. Depending on the direction of travel of the voltage wave, the current wave is going to adjust its sign, that is what it says, right. If the voltage is going to travel forward, the voltage and the current are going to be of the same sign. If the voltage is going backward, the voltage and current are going to be of the opposite sign. This is a phenomenal piece of information, alright. If you go back to your general solution for the transmission lines, okay, we had f plus of t minus z by u plus f minus of t plus z by u to be the solution for the voltage. So, f plus of t minus z by u plus f minus of t plus z by u is what the current would look like, right. So, the current is actually doing weird things and it is adjusting itself to that direction. Now, let us notice more things, okay. I will run this again. This time I am going to increase the amount of time, I am going to run it. The voltage is going along the transmission line to the left and the right end, right, alright, almost hit the boundary, okay, almost hit the boundary. So, now is a very critical stage. I am going to make it go a little longer and try to understand what happens. So, the voltage is travelling to the left and to the right. Okay. Now, that is something phenomenal. The impulse on the right hand side bounced from the edge and flipped its sign. However, the voltage wave on the left hand side did not change its sign. It tells you that something is happening to the boundary. So, the boundaries can reflect, but they can also alter the sign of the reflection. So, I think in our mind we are starting to already figure out where we are going. We are trying to understand the term reflection coefficients, right. The reflection coefficient is going to be having a magnitude and also going to be having a sign is what we are indirectly saying. Same way, if you look at the bottom graph for current, the current actually did not flip on the right side, but it flipped on the left side. So, something is happening. So, when the voltage flips, the current does not flip. When the current flips, the voltage does not flip. This means that we need to understand what is going on these edges. Okay. So, it also means that a boundary condition would affect voltage in one way. The same boundary condition would affect current in some other way. Okay. So, and we need to understand what the voltage profile and current profile in a transmission line would be given some set of boundary conditions. And here we are going to start with some very simple boundary conditions, alright. We can start with say a transmission line is broken, it is an open circuit, or since you have two conductors, a transmission line can have a short between the two conductors. Say some piece of metal is touching both these pieces and you have a short circuit. These are the two extreme cases, alright. So, either you have an open circuit or you have a short circuit. These are the two boundary conditions that one can have in a transmission line to begin with. And clearly I can make out that maybe that because the voltage did not flip on both the sides, on one side I am having one condition, on the other side clearly I am having other condition. Since the current did not do the same thing on both the sides, the conditions are different. I think we need some analysis. We will go back to our theory and try to find out more about reflection coefficients and things. Now, what you are seeing here can be used for many purposes. Imagine that you have a transmission line that has some open or short circuit at the end. Maybe you have a way to find it. All you need to do is send a pulse, wait for the pulse to come back. If the sign of the pulse is flipped, you can figure out what is going on. If the sign of the pulse is not flipped, you can figure out what is going on. So, in other words, you can detect whether the line is actually having a short circuit or an open circuit on the other end. It's a very important thing. You can have a 1 kilometer long transmission line, and I want to figure out if there is an open circuit or a short circuit. All I do is send a pulse, I wait for the reflection. When the reflection is positive, I can make out something. The reflection is flipped, I can figure out something. All right. So this is practically used to detect faults in cables actually. Okay. So we'll stop here. We'll go back to the theory in the next class, try to build on this, and then we'll come back with the computer part, and then we'll keep augmenting one and the other. Right. So we'll stop here.